When we look at this video, we don't see a sequence of independent pixel grids, but a bear moving in its environment as the camera pans. Our goal is to represent the video in terms of these scene elements, and to relate the instances of these elements over the entire video. To do this, we introduce Deformable Sprites, a layered video representation. For a video, we accumulate the appearance of each scene element into a shared texture image, or sprite. At the same time, for each video frame, we find instances of each sprite, and map each instance in the sprite's UV coordinates with non-rigid transformations. We can then use these components to reconstruct each frame of the video. We can also add consistent edits to articulated objects. Notably, we do this without any input masks or supervised training. Prior works have explored this task of video decomposition for video editing applications, but have all relied on input masks of the objects of interest. We study the joint problem of estimating the masks and appearances. For each video, we represent the appearance of each layer as a fixed texture image. Then, for each frame, we predict masks of each sprite instance, and estimate a non-rigid transform from the frame into the sprite's UV coordinates. We can then compute the appearances of each layer to reconstruct the input frame. We optimize the sprite images through a shared generator network with fixed random codes. We use a separate shared network to predict layer masks that are consistent with appearance cues over time. Finally, we estimate a non-rigid transform that maps each pixel of a frame to a UV coordinate in the sprite image. This allows us to remap each frame's appearance from the global sprite images. For each frame, we combine a perspective planar transform and a 2D B-spline warp for the transform to be low-dimensional and spatially smooth. For the entire video, we keep a small set of keyframes to model a smooth trajectory over time. We then optimize our representation with per-frame losses on the reconstructions and additional flow-based losses to supervise the mask grouping and transforms. For the background mask, we first use the flow correspondences to estimate epipolar geometry and the per-pixel Samson distance. We then penalize the points in the background mask with high Samson distance that cannot be explained well by camera motion. Then for each foreground layer, we minimize the difference between the layer's flow to its mean, similar to k-means clustering. We supervise the transforms with a flow consistency loss, namely optical flow maps a point x in frame t to x prime in t+1. The transforms then map both frames into the shared coordinate system of the global sprite image. X and x prime correspond to the same underlying scene point and should therefore go to the same point in the sprite image. We now show our method in 3 settings: benchmark videos, internet videos with non-traditional objects, and editing applications. Although our approach recovers more than the per-frame masks, our output masks are competitive with or better than state-of-the-art unsupervised segmentation baselines. In addition to the masks, our method gives high-quality decomposition. We recover our deformable sprites based solely on the motion and appearance cues present in the input, and do not rely on any training data. As such, we can easily recover deformable sprites for objects that do not fall into common categories. Like clouds, snails, and bees. Our method can also handle scenes with multiple moving objects. Finally, we demonstrate video editing applications using our Deformable Sprites decomposition. By directly editing our sprite images, we can consistently propagate edits across the entire video. Note how the logo deforms with the articulated foreground. Here, the edited moving layers are consistent with occlusion effects. We can also swap out the sprites entirely with a style transferred version. We can also make motion sculptures of the moving foreground. Our method struggles to segment out parts of the body that are static over the entire video, and also cannot model well drastic changes in lighting. And the number of layers must be well specified. Here, the two parrots are grouped into the same layer. However, when we add an additional layer, they are well separated.